In this video, we will cover many angular motion variables and solve problems using these variables. So let's say we have a ball attached to a string and it travels from here to here in 1 second. And we ask ourselves, how much angle has this ball traveled? Well, this is called our angular displacement, and we denote this with a delta theta. And our angular displacement equals our final angle minus our initial angle. And we typically measure our angular displacement in radians. So back to our problem. Our angular displacement for the ball is going to be our final angle, which is at pi over 2 radians, minus our initial angle, which is at 0 pi radians, to give us a total of pi over 2 radians for our angular displacement. And our angular displacement is analogous to solving our linear displacement, which we defined as our final position minus our initial position. Now that we figured out how to find our change in angle, what if we wanted to know the rate of which our angle was changing? Well, in terms of linear quantities, we define the rate of an object's change in position as the velocity, which equals the object's displacement divided by a change in time. And using this pronotation, we can define our angular velocity, which we denote with the Greek symbol omega, to equal our angular displacement divided by a change in time. And the units for our angular velocity is radians per second. Now, we can find the ball's angular velocity by plugging in what we know. So we know that the ball's angular velocity equals its angular displacement, which we found out to be pi over 2 radians, divided by a change in time, which we know that the final time was at 1 second and its initial time was at 0 seconds. So our ball's angular velocity equals pi over 2 radians per second. And for our last angular motion variable, we have our angular acceleration. Just like our linear acceleration, which was defined as a change in velocity divided by a change in time, our angular acceleration, which we denote with the Greek symbol alpha, is going to equal the change in our angular velocity, so the change in omega, divided by a change in time. And we measure our angular acceleration in radians per second squared. Now, let's look at a problem. In this problem, we have a tennis ball that's being swung from here to here in 2 seconds, and we are told that the initial angular velocity is 0 radians per second, and our final angular velocity is pi over 2 radians per second. And we are asked to find the ball's angular velocity and angular acceleration. Well, we know from the lecture that the angular velocity's formula is omega equals our angular displacement divided by a change in time. And just by looking at our diagram, we know that our angular displacement is going to be pi over 2 radians. And we know that our change in time is going to be 2 seconds. So our angular velocity is going to be pi over 4 radians per second. Now you may be confused because this omega does not correspond to either our initial angular velocity nor our final angular velocity. And that is because this omega is our average omega, or our average angular velocity. Now let's solve for our angular acceleration. From the lecture, we know that our angular acceleration is alpha equals the change in our angular velocity divided by a change in time. And we know that this simplifies to our final angular velocity minus our initial angular velocity, all divided by a change in time. So now we can plug in our known variables. We know that the final angular velocity is pi over 2 radians per second. And we know that our initial angular velocity is 0 radians per second. And this is all divided by our change in time, which is 2 seconds. And we can simplify this to get that our angular acceleration equals pi over 4 radians per second squared. And yes, technically this is our average angular acceleration. But if the angular acceleration is constant, which in almost all cases we will look at, then our average angular acceleration will equal our instantaneous angular acceleration. So in recap, our angular displacement is denoted as delta theta and is defined as the change in angle. And to find our angular displacement, we subtract the final angle minus the initial angle. The angular velocity is denoted as omega and is defined as the rate of which an angle changes. And to find our angular velocity, we divide our angular displacement divided by a change in time. And the angular acceleration is denoted as the Greek symbol alpha and is defined as the rate of change of the angular velocity. And to find our angular acceleration, we divide the change in angular velocity divided by a change in time. And one thing I forgot to mention in the lecture is that when we're traveling counterclockwise, we consider that to be positive. And when we're traveling in the clockwise direction, we consider that to be negative. Thank you for watching this video and hope to see you next time.